Now we'll see some properties of these recursive and recursively enumerable languages. First we begin with recursive languages. When you have two recursive languages L1 and L2, then their union is actually recursive like regular. We have seen properties of regular language, right? In the same way we can see recursive language properties. Two recursive languages union is recursive, their intersection is recursive, and their complement is recursive. Okay, so recursive languages are closed under union and intersection and complement. We'll see what is the reason for that. We have a construction for everything. First of all, ask yourself, what is a recursive language? Whenever a language is recursive, then that language will have Turing machine, a total Turing machine for it, correct? So for that, always, if example, this is language 1. Now a string x belongs to L1, then if I give that string to this total Turing machine, because this is total Turing machine for L1, then if x is given, really x is part of L1 or x belongs to L1, total Turing machine is going to go to S state. S state means final state. And if x does not belongs to L1, then x will go to non-final state, definitely R state. That means, did you remember reject state? So that means no state. From now onwards, yes means your Turing machine goes to T state, no means it goes to reject state. That is what my intention. So whenever you have total Turing machine, that's why always we can answer about whether x belongs to L1 or x does not belongs to L1. So with that Turing machine, we are going to solve this problem. L1 union L2 is recursive. Why? Because already L1 is recursive, L2 is recursive. Then for L1 union L2 language, I am going to construct a total Turing machine. How you see? So that this is the total Turing machine for L1 union L2. Whatever the input is given x, then I run here because I use two sub functions. Okay. So function number 1 is nothing but a code of L1. That means L1 has a Turing machine, right? Total Turing machine. So let's call it as Turing machine of L1. Let's say that it is a total Turing machine for L1. This is total Turing machine of L2. Whatever the input is given to this total Turing machine, this is total Turing machine for L1 union L2. If x belongs to L1 union L2, how I am going to accept? First of all, I will tell you the requirement. Really, it is a total Turing machine for L1 union L2. If x belongs to L1 union L2, what it should do? It should go to S state, right? That means final state. If x does not belong to L1 union L2, this total Turing machine should say no, I don't accept. Such total Turing machine we need. For that, I take help of L1's Turing machine, L2's Turing machine. I take input x. Already I have in my finite control, already I told you, we can have a Turing machine's code as part of our machine's code, correct? So I give this input x to this total Turing machine at a time. How you give? Simple. I run this code for one step, this code for one step. In that way, parallelly I can run. So that is nothing but my total code. Okay. So if at any part of time when I am simulating this total Turing machine of L1 on X, if it goes to a accept state, okay, let's use yes and no, easy for us, yes and no. This total Turing machine also will have yes and no. Okay. Now whenever I give X input to this total Turing machine and this total Turing machine, if this says yes or this says yes, because L1 union L2, right? If at least one Turing machine accepts, then I will accept. I say I will go to final. So this is the description of this final total Turing machine, right? Now, sir, what if X is rejected by this code? No problem. Then I am also running this code also, right? If both reject, what I do is I check, I remember one thing. In my finite control, I remember whether this total Turing machine does what. If total Turing machine L1 rejects my L1, this total Turing machine also rejects, then only I reject. Understand? Yes. So at least one of them accept, then I accept. Here be careful. If at least one of them accept, I accept. Both of them reject, then I reject. End of the day, what is going to happen is, really X does not belongs to L1 union L2. This total Turing machine L1 is going to reject it. This total Turing machine is going to reject. Then finally I can reject. In that way, always I can decide whether X belongs to L1 union L2 or not. Correct? So there is a total Turing machine for L1 union L2 also. I don't really require to loop, correct? Do we need a loop? No. So when X belongs to L1 union L2, I can definitely find it out. How? By help of my brothers L1 and L2, correct? So L1 definitely will accept it, L2 also will accept it, correct? Sorry, because X belongs to L1 union L2, either this X will be eventually will be accepted by L1 or L2. One of them is definitely going to final state after some finite number of steps. There is no loop, correct? Eventually, after some point of time, one of the Turing machine goes to final, then I go to final. So I am going to final is confirm whenever X belongs to L1 union L2. What, sir, if X is rejected by your both Turing machines? Then I will go to reject state. In that way, so I can construct a total Turing machine. So L1 union L2 is recursive. Now with the same spirit, this time quickly we compute Turing machine for L1 intersection L2. Why L1 intersection L2 recursive is, I am going to construct, you see. This is the total Turing machine for L1 intersection L2. I take the help of again two brothers L1 and L2. Okay. So whenever we give input to L1, let's say L1 means L1's Turing machine, this is L2's Turing machine, then I am given input X, I will distribute that input to both Turing machines. That means I run simultaneously, one step here, one step here, and I copy these two codes into my finite control. So I simulate L1 one step, L2 one step, L1 one step, L2 one step, eventually. So really X is part of L1, then it will accept. If X is part of L2, L2 also will accept. So I remember it. So whenever L1 accepts and L2 accepts through my finite control, I remember it. That means I mark them in my tape like this. Whenever X accepts, I put a mark. If L2 accepts, then I put a mark. Whenever there are two marks, I can count it, right? Your Turing machine can count number of symbols. So using that, if both Turing machines accept, then I will go to final. So I say yes. If one of them rejects while simulating, then automatically I will go to reject state. That means in my overall Turing machine I will go to reject state. That means I will go to no. That means if this is no and or this is no, no or no. Here yes and yes. Remember it. Yes and yes, yes. No or no, no. In that way again we can construct yes no machine. That's why L1 intersection L2 is recursive. Now L1 bar already we proved it, right? So whenever L1 is recursive, we can create L1 bar as a recursive machine, correct? How to do that? Simple. This is your recursive machine. So you have yes and no. Then I use bigger machine for L bar. So this is for L. I give input X to L. If X says yes, then I say no. If L says no, then I say yes. In that way, so by doing the complementation we can do it, right? So L1 bar is recursive. This is about recursive languages. Now we will see the same story about recursively enumerable. Okay, now we'll see closure properties of this recursively enumerable languages. L1 comma L2 are recursively enumerable, then L1 union L2 is recursively enumerable. Yes. Why? Because example, let's say you have already Turing machine for L1, correct? That's why it is recursively enumerable language, but I don't know whether it is total or not. So that's why for safely we represent like this. So this is the Turing machine for L1. So if input is given, what are the behaviors it can have? It will say sometimes yes for the right input. For wrong inputs, it may go to reject state. That means it may say no, otherwise it may be still in the loop. Okay. So this is representing infinite loop. Now there is another Turing machine for L2. Given input, if really it gets a right input, that means if it gets an input which belongs to language L2, then this L2 Turing machine is going to definitely accept eventually. I don't know when, but definitely there is no infinite loop at that time. So if X does not belongs to L2, then sometimes it is going to say no, but sometimes it may go into infinite loop. Now see, really there is a Turing machine for any language L1. Now I would like to clearly tell the cases. If you give an input here and that X belongs to language L1 for which you have designed a Turing machine, then 100% that Turing machine is going to accept that input. If X does not belongs to L1, then your Turing machine has two cases. Your Turing machine might go to reject state, and because of that it can reject it. Otherwise, still it may be in infinite loop. Okay, there are two possibilities. So this is infinite loop. So such Turing machines we have for L1 language and L2 language. Now we have to construct a Turing machine for L1 union L2. Constructing a Turing machine for L1 union L2 means if an input X which belongs to L1 union L2 is given, what we should do? 100% we should accept. If X does not belongs to L1 union L2 is given, then we can do anything. That's why let me focus on only right inputs. For right inputs, if you design the machine, that is enough. So really, if you are constructing a Turing machine for L1 union L2, because it is not total Turing machine, its responsibility is if the string belongs to L1 union L2, where L1 and L2 are languages, then X belongs to L1 union L2, definitely we should accept. For that, what I am going to do is, I am going to construct a Turing machine for L1 union L2. It looks like this. So given input, what I do is, already remember one thing, I have a code of L1, I have a code of L2. I run them simultaneously. One step of L1 code, one step of L2 code, one step of L1 code, one step of L2 code. So eventually what happens, since X belongs to L1, sorry, what is the definition of L1 union L2? Whenever a language is union of two languages, then if X belongs to L1, then definitely X belongs to L1 union L2. If X belongs to L2, then X belongs to L1 union L2. Can I say one thing? If either this machine or this machine accepts, then definitely X belongs to L1 union L2 and I have to access. That's why I put a OR condition. Just symbolically I'm showing that. That means one of the Turing machines go to final state, then overall Turing machine goes to final state. Yes, one of them goes. If none of them goes to final state, then I don't go to final state. That's it. I don't want to talk about no and reject loop. Now for remaining inputs, in other than this case, for remaining things I can do anything. Still, if you want clarity, if you want to write a better Turing machine, what you do is, if Turing machine L1 says no, L2 says no, if both says no, L1 no and no, then you also go to no. If this Turing machine is in loop, this Turing machine is in loop, then you will be in loop. You can be in loop. In that way, we can design a Turing machine. This is important for me. So construction of no and loop is not really important. Remember one thing, whenever you construct a Turing machine, if that is a Turing machine for a language L, if the string which belongs to that language is given, definitely we should accept. Such a functionality we have to provide. If X does not belong to that language, you can do anything. You can loop, otherwise you can reject, but you should not accept, right? So this is the final construction, right? Example, we'll check. Example, let's say really X belongs to L1 union L2. What happens, we'll see. What is my target? I should accept. For that, I will give like this. I simulate L1 for one step, L2 for one step simultaneously. Since assume that let's say really X belongs to L1, then eventually, so L1 will accept it. Correct? If L2 X belongs to L2, then eventually L2 also accepts, because it is OR condition. Then one of them accepts, you are accepting, definitely will accept. Correct? So that's why this construction will work 100%. Whenever your string belongs to L1 union L2, this Turing machine is going to accept. That's enough. Now second one, L1 intersection L2. For that also we can construct a Turing machine. This time little bit fast I go. You have a Turing machine for L1, you have a Turing machine for L2, then I am going to construct a Turing machine for L1 intersection L2. Here these two are codes. Okay, this entire Turing machine is nothing but a code. In this code, these two are the part of the codes. Okay, when given input X, what I do is, first I run L1 for one step, L2 for one step using my Turing machine, right? So this is called simulating L1 and L2. Did you remember? Universal Turing machine was simulating lot of Turing machines, correct? Here I am only simulating L1 and L2. Okay, now X belongs to L1, eventually while running after some time, after finite amount of time, definitely really X belongs to L1. L1 will accept it after finite amount of time. It won't take infinite time. Why? If it is taking infinite loop, then only it takes infinite amount of time. If it is in taking infinite loop, then definitely it is not going to accept. But really X is a L1 is a Turing machine for this X, then definitely it should accept it, correct? So that is a property of that. So again let me write first of all states accept no loop. Here accept no loop. So whenever a string belongs to L1 intersection L2, it belongs to L1, it belongs to L2. But this Turing machine is going to tell us whether X belongs to L1 or not, correct? Because we have such Turing machine. That's why this accept, whenever these two Turing machines accept, then I will go to accept state. That means I am talking about L1 intersection L2's functionality. If one of them rejects, okay, then automatically, so I am going to reject, correct? No and anything. So if I get no here, then I will go to no state. That's why. And one more thing, I don't really require to define functionality of no, correct? So really whenever I'm defining a functionality of simple Turing machine or ordinary Turing machine, only for acceptance if I write the code, that is enough, correct? Second thing, if you want to write a sophisticated code, we can write remaining things. What do you want to do? What do you want to do really? If this Turing machine and this Turing machine, if both are in loop, you also will be in loop. Okay, such way I am constructing. Sir, one of the Turing machine says no, then I will go to no. Okay, such a way we have to plan, right? So then definitely whenever a string belongs to L1 intersection L2, you will be coming to accept state. Why? Because really X belongs to L1 and L2. This will come to accept state, this will come to accept state. Sir, what if they take infinite time? They don't take. Then that is not a Turing machine for that language. Okay. Whenever you want to say that I have a Turing machine for some language, if you give a string of that language, then your Turing machine should accept infinite amount of time. Otherwise, it's not a Turing machine. Example, I will give you one analogy. You are writing a program for factorial. Then I asked you to compute 5 factorial. My input is 5. Then really your program is for factorial, then factorial of 5 should be 120, but your function is not working, it is in infinite loop. Is it a right program? No, really it's a factorial is a right program. If I give input 5, then after finite amount of time it should give 120. If it takes infinite time, that means it is not giving output. If it is not giving output, that is not a factorial program. Understand? In the same way this one. Now the last one, we know this one. L1 bar may not be recursively enumerable. Okay, that means when you have a Turing machine for a language, then we may not have a Turing machine for its complement. Why? Because sometimes that complement may not be recursively enumerable. Example I will tell you. M hash x, this is one language where M halts on x. Second one, M hash x such that M does not halt on x. Let's say this is language L. Of course, that is halting problem. This is, I mean, there is no name for it. So this is L bar, correct? Halting problems complement. Everyone read it. All the strings where M halts on x. These are all strings where M does not halt on x. In the world, a Turing machine either halts on x, otherwise does not halt on x. Then, so only two cases exist. So these are all strings where M halts on x. These are all strings where M does not halt on x. So these two are quite opposite, otherwise, mutually exclusive. Then if, what is this language? Recursively enumerable, we know that, but not recursive. And what is this language? Already I proved that it is not recursively enumerable. Now, you have a language L which is recursively enumerable. Its complement not recursively enumerable here in this case. Then can you construct a Turing machine for this? No, because for non-RE, that means a language is not recursively enumerable, we cannot construct a Turing machine. That's why here when a language L is recursively enumerable, it is not compulsory that L bar also recursively enumerable. Sometimes it may be non-RE. Then can I construct a Turing machine for L bar? No. That's why sometimes I can construct, sometimes I do. That's why there is no construction. Understand? So remember one thing. So finally this property, whenever L1 is recursively enumerable, then L1 bar may be RE, may not be RE. That is a property, remember it.